the study of the physical foundations of hemodynamics with a number of issues, and in particular, we will consider the conditions of continuity of a jet or stream. We will study how the blood flow velocity is distributed in a large circle of blood circulation. Let's look at parameters such as internal friction, and accordingly, the mathematical patterns that accompany this phenomenon. The types of flow are laminar turbulent, also a number that allows you to calculate the nature of the flow, and a large volumetric question. Distribution of blood pressure in the large circle of blood circulation, plus methods of measuring blood pressure. Before we proceed directly to the issues of hemodynamics, a few words about which sections of physics this science is connected with. Hemodynamics itself studies the movement, patterns of blood movement through the vascular system. Hemodynamics is based on such a process, or rather such a science as hydrodynamics. Hydrodynamics, in turn, studies the laws of motion of liquids and the interaction of liquids with solids. In other words, hemodynamics also studies the properties of blood and the properties of blood vessels and the patterns of blood movement through the vascular system in closed circles of blood circulation. Before we go directly to one of the groups of indicators that characterize blood circulation, let me remind you of a few basic concepts related to fluid, and in particular to blood. So, the liquid can change its shape. Unlike solids, a liquid takes the form that has the shape of the vessel in which it is located. That is, due to the displacement of liquid particles, changes in the external shape occur. A real liquid is a compressible liquid. That is, a real liquid can slightly but nevertheless change its volume, albeit within insignificant limits. Compared to a gas, for example, a real liquid is compressible up to several percent relative to the original volume. A real liquid has a viscosity, that is, a moving liquid always experiences friction, the so-called internal friction, that is, resistance from other stationary structures, for example, the walls of a pipe or the walls of vessels. The main regularities in hydrodynamics are formulated precisely for ideal liquids, that is, liquids that do not compress, and liquids that have internal friction or viscosity equal to zero. According to their parameters, such liquids as ether, acetone, alcohol, and, with a large assumption, water, are close to the concept of an ideal liquid. I repeat, if hydrodynamics deals with the laws of motion, well, mostly water. Moreover, water as an ideal liquid, then hemodynamics studies the basic patterns of blood movement through the vascular system. There are two groups of indicators in hemodynamics. This is an indicator of speed, speed characteristics, and characteristics that determine, influence, change pressure, blood pressure. We turn to the first group of speed parameters and consider with you the basic law, which is not even legal because the regularity, which, of course, was originally formulated for an ideal fluid. So, according to the condition of continuity of the jet, or the condition of continuity of the flow, an equal volume liquid flows through any sections of the pipe at equal intervals of time. Please note that an additional characteristic appears in hemodynamics, the so-called volumetric velocity. In contrast to the linear velocity, that is, the speed of movement familiar to us, which is calculated as a path for time, the volumetric velocity of the liquid corresponds to the product of the linear velocity by the pipe section, that is, the volumetric velocity is the volume of liquid flowing per unit of time through a given section. So, in order to preserve the continuity of the flow, that is, the continuity of the flow, the continuity of the jet, it is necessary that the volumetric velocity of the liquid be maintained constantly at any part of the fluid movement. Look at the figure in the first block of this example. The section with 1 is indicated. That is, put yourself a liquid moving at a speed of 1 through a given section, of course, occupies a certain volume, and the same volume, in order to preserve the continuity of the jet, must be moved through the place of narrowing, that is, through a pipe with a section of C2. Well, of course, in order for the same volume of liquid to pass through this narrowing, it is necessary to increase the speed. And it turns out that how many times the cross-sectional area or diameter will decrease in the end. The speed of fluid movement will increase by so many times. The situation is as follows. When the liquid from section C2 will move to section C3. In this case, in order for the liquid to occupy the entire volume provided to it, that is, in order to occupy the entire area of the pipe, it must slow down, otherwise it will form. Cavities may form in the place of fluid movement. That is, if the liquid moves at the same speed, then part of the pipe will remain unfilled. But in order, I repeat, to maintain the condition of continuity of the jet, it is necessary to slow down the speed of fluid movement, and by as many times as the cross-sectional area of the pipe increases. So, the very condition of continuity of the flow, I repeat, is that at equal intervals of time, an equal volume of liquid flows through any section of the pipe. That is, the conditions are met for continuity, to preserve the continuity of the flow, that is, the flow without the formation of a cavity. The mathematical conditions for the continuity of the jet look how Q equals the product of the cross-sectional area by the linear volume and equals a constant. That is, here they are the equivalent products of the area by speed for the first section, the area by speed in the second section, and the area, the cross-sectional area by speed in the third section. That is, only in this case, when all these products are equal, the liquid will be able to move in a continuous flow. Let me remind you that these are the necessary conditions for normal blood circulation. In other words, the condition of continuity must be fulfilled, in hemodynamics, of course. At first glance, the conditions of continuity of the hemodynamic flow are exactly the opposite. Well, we remember, yes, that in the thinnest vessels of the capillaries, the blood moves at the lowest speed. But speaking about the fulfillment of the conditions of continuity of the jet in hemodynamics, of course, it should be borne in mind that the cardiovascular system in particular, we will consider, for example, a large circle of blood circulation. It is a closed, branched vascular tube. That is, all the blood that is pushed out of the left ventricle and enters the aorta in a large circle of blood circulation. It's blood. Then it spreads through the arteries. Then the arteriole fills the capillary network. Then venules merge from the capillaries. Then veins. That is, the same volume circulates through a closed circulatory system and at the same time. A necessary condition for normal operation, for normal life activity, is the continuity of blood movement. In order to avoid the formation of gas bubbles, there is a different kind of embolyte. Therefore, when we make calculations to fulfill the conditions of continuity of the hemodynamic jet, we do not consider individual vessels, but the total cross-sectional area. The section is at an appropriate distance from, say, the heart. I'm going to flip through it now, and then we'll go back to the previous equation. Look here in front of you. Well, a very schematically depicted closed vascular system, that is, the aorta, arteries, arterioles, capillaries, venules, and veins. There should be two. So, returning to our equation, the flow continuity conditions for, let's say, a network of capillaries should look like this. The total cross-sectional area of all capillaries is as much as the cross-sectional area of the aorta. How many times the velocity in the aorta exceeds the velocity of blood flow in the capillary? This ratio is approximately equal to 700 or 800 dimensionless units. That is, the area of all capillaries is about 800 times the cross-sectional area of one aorta, and accordingly, the speed of blood flow in the aorta is also 800 times greater than the speed of blood flow in the capillary. The ratio is approximate, since the conditions of continuity for hemodynamics are not included, of course, the conditions of elasticity of the tubes. In other words, we believe that the tubes are absolutely rigid, not elastic, and therefore the conditions of continuity of the jet are approximately applicable to the real circulatory system of a person. It is performed on shorter sections of the vascular system, but in general it is performed approximately. Here is a schematic change of two parameters that are marked in the condition of continuity of the jet for hemodynamics. Here are two graphs. The upper graph is a graph of the cross-sectional area distribution. That is, here is the total cross-sectional area of all vessels. Here it is, the aorta is almost near zero branching arteries. Very fast branching in the arterioles. The relative change in the number of vessels in the capillary area, well, more precisely, the transformation of the area, and then the vessels merge into venules, that is, the total area decreases and the vena cava. This line, generally speaking, should have passed a little higher, because the area of the hollow veins is, of course, larger than the area of one aorta. Due to the change in the cross-sectional area of various sections of the vascular bed, the speed of movement also changes. Pay attention to the lower graph. In the lower graph, the first point I'm pointing to now is the blood flow rate in the aorta. Even in a state of physiological rest, this speed can be, well, 52 and up to 1 meter per second there. That is, the red blood cells in the aorta, even when we are in the absence of physical activity, move at a speed of half a meter to a meter per second. This is the maximum speed of blood movement on the cardiovascular system. Then, as you move along the aorta, well, the large main vessels, look, the speed drops. A significant slowdown in the blood flow rate is observed when crossing the border of the artery of the arteriole dash. The maximum angle of incidence, namely at the transition from arteries to arterioles, well, you can also look at the top picture, and it is at this border that there is a sharp increase in the number of arterios. In other words, there is the most noticeable branching, that is, the sharpest increase in the number of vessels in the large circle of blood circulation. The number of arterioles is, well, quite long, but already thin vessels grows very quickly. The blood flow rate drops, look, almost to zero. This drop continues in the capillary network with a minimum blood flow rate. Well, remember how fast the blood flows out, let's say, when it is taken for analysis from a finger. In other words, these are fractions of millimeters per second or a few millimeters per second. Then, after passing through the capillary network, the blood flow rate begins to increase. This increase is due to a decrease in the cross-sectional area. That is, the entire volume of fluid that was released from the left ventricle and passed through the aorta, then spread to the arteries arterially, and so on. The same volume of liquid, having passed the widest capillary network, drains, merges into venules and, relatively speaking, for a smaller deformation, it is necessary, of course, to accelerate the speed, increase the speed of blood movement for further movement when the conditions of continuity of the flow are met. Note further in the hollow veins, the blood flow velocity increases relative to the speed of movement there in the capillary network, in the venules, but it is, nevertheless, this speed is less than the speed of blood flow in the aorta. Here is a change that is due to the fact that blood is not an ideal fluid. That is, Blood is a structured liquid, and therefore the friction force and resistance that the moving blood overcomes through the vascular system leads to the fact that part of the kinetic energy that the blood possessed at the exit from the aorta is lost, and therefore the speed of blood flow in the aorta does not exceed, of course, half a meter per second. I ask you to remember the reasons for the sharp drop in blood flow velocity in the area of the arteriolar artery. Here in this paragraph, both reasons are indicated, for which there is a sharp speed reset. This is growth, this is a significant increase. The total cross-sectional area, that is, the area provided for filling with blood, increases sharply, and the second condition is an increase in wall friction. That is, more and more liquids have to interact with fixed vessel walls. Naturally, the same kinetic energy is spent on this, and due to this, the speed is also reset. This is how the conditions of continuity of the hemodynamic jet or the conditions of continuity of the flow are fulfilled. Do not forget that we are talking about blood after all as a real liquid. Here in front of you is the very phenomenon that determines the properties of blood in many ways. This is internal friction or viscosity. Well, we are still considering the concept, regardless of hemodynamics. In hydrodynamics, the viscosity of a liquid is determined by the forces of attraction between the molecules of a liquid, or the coupling of molecules. Well, sometimes they talk about the adhesion of molecules to each other, and between molecules and the fixed walls of a vessel or pipe more precisely. Viscosity or internal friction is the ability of a liquid to resist the displacement of particles. Viscosity always hinders the flow of liquid and, of course, always reduces the speed of movement. The phenomenon that, well, which we are talking about, this is a decrease in the velocity of fluid movement due to viscosity, was studied by Newton. The model that is used in the study of the viscosity phenomenon is a pipe. Well, here are the walls of the pipe, what you see at the edges. There is a moving liquid inside the pipe. The red arrows indicate the velocity of the fluid. The maximum velocity of fluid movement is observed along the axis of the pipe or in the center. The minimum velocity of fluid movement near fixed walls. That is, if we mentally divide the entire provided volume or cross-sectional area of the pipe into many layers, then here is the very first layer, a layer thickness of, say, 1 molecule. It will simply stick to the stationary wall, and its speed will be 0 or almost 0. Then the next layer, which is carried away by a moving liquid, has a speed, that is, it is slowed down by the first layer and accelerated by the next layer. And as a result, it turns out that the fluid moving in a closed pipe distributes its speed of movement according to a parabola. Here is the pattern that Newton determined, just connects the friction force that occurs between moving layers of liquid with different speeds. This friction force depends primarily on the viscosity of the liquid. With this letter it reads this: the viscosity of the liquid is determined. A value that depends on the molecular properties of the liquid and on the state of the liquid. Then, the second factor, which Newton put into the equation characterizing the friction force, is the so-called velocity gradient of the dV/dx. We can call this value the velocity shift. Well, the velocity gradient is the most accurate definition of what we can observe when different layers of liquid move at different speeds. In other words, the more the speed of movement of one layer differs relative to another, and the closer, say, these layers are placed to each other, the greater the friction force will be. Particles that move at different speeds will experience a greater friction force. In other words, there will be both coupling and uncoupling between these molecules moving in adjacent touching layers. And finally, C is the contact area. That is, in this case, C is not the cross-sectional area of the pipe, but the contact area. In other words, the more molecules interact with each other, yes, and at the same time, moving at different speeds, it experiences this friction force, the greater the total friction force will be in the end. Next, the viscosity coefficient, as I have already said, is read as a Greek letter and is defined as a value equal to the friction force acting on 1 square meter of the contact area of the moving layers with a velocity gradient equal to 1. That is, if two layers of a moving fluid interact on an area of 1 square meter, and the velocity shift is 1 meter per second between these layers, then this value will characterize, then this is the friction force, and will characterize the viscosity of this liquid. Traditionally, viscosity is measured unconventionally, more precisely in the C system, measured in pascals per second, but it is still possible to be able to meet units as often as possible, such units of viscosity measurement as poise in the old-fashioned way. And finally, the most important thing for any liquids is the viscosity coefficient, or the viscosity depends. Write it down and remember it. First of all, it depends on the molecular properties of the liquid, that is, on these very forces of adhesion, the forces of intermolecular interaction. And secondly, on the state of the liquid. Well, the state of the liquid is mainly influenced by temperature. Remember how the same substances, let's say oils, can behave when the temperature changes. At a temperature close to zero, it is practically a solid. When heated, it is less viscous, and at significant heats, it is already a very, very fluid liquid. The next feature concerning the viscosity of a liquid is the division of liquids into Newtonian and non-Newtonian. This means that liquids whose viscosity depends only on temperature and only on the kind of liquids are called Newtonian. Such liquids include homogeneous liquids. Newtonian liquids, I repeat, include homogeneous or simple liquids: water, ethyl alcohol, acetone, ether. Newtonian fluids. Why are they Newtonian? Because they obey Newton's law or Newton's equation. Liquids whose viscosity also depends on the speed of movement, or, more precisely, on the mode of movement. They are referred to as non-Newtonian liquids. These are liquids that consist of complex and large molecules, for example, proteins, cells, polymer solutions. Blood is also referred to as non-Newtonian fluids. Blood, because it is a composite fluid that contains red blood cells, platelets, leukocytes. Well, basically the properties of blood as a non-Newtonian fluid are determined by the properties of red blood cells, not platelets, and white blood cells, proteins, namely red blood cells. So, it means that non-Newtonian liquids, unlike Newtonian ones, can change their viscosity parameter depending on the speed of movement. The direction of change in viscosity. In general, it is so unambiguous. As the fluid velocity increases, the viscosity of such liquids decreases. This is explained, first of all, by a change in the structure of the substance. Here, as an example, it is written that high molecular compounds are referred to as Newtonian liquids. Here are the same polymer solutions. So, if a liquid containing long-chain molecules is forced to move at a very high speed, these longest chains will simply start to break. That is, it will decrease in length, and thus the viscosity will fall. Well, another thing is that when a slowdown occurs, these polymers are unlikely to be structured in the opposite direction, but nevertheless. But with blood, this is possible. Take a look at the next slide. Why blood is not a Newtonian fluid, I have already said. And here's how the viscosity of blood changes with a change in the speed of blood flow we will now consider. This means that the blood moving through the main vessels moves fast enough. The red blood cells practically do not interact with each other. The denser red blood cells are placed close to the axis. The central axis of the vessel is less dense near the walls. And here's what happens when the blood moves through the bottlenecks of the cardiovascular system. That is, red blood cells. Well, before you, of course, such a model is already a pathology of blood, when almost all red blood cells have entered into some kind of association with neighboring ones, forming such coin columns. This may not be the most typical example, not the most visual, but nevertheless. Red blood cells, moving at lower speeds, have time, so to speak, to interact with other red blood cells. And even two red blood cells, moving together, already create more, experience more resistance from the environment. That is, the narrowest areas of the snowvascular system are capillaries. That's exactly where this kind of conglomeration occurs. That is, red blood cells, moving through narrow areas, unite, stick together, you can say so, and thereby the viscosity of this liquid increases. That is, the longer the chains of red blood cells, the higher the viscosity of such a liquid will be. Then, when the blood from the capillaries moves into the venules and the blood flow rate increases, due to the fulfillment of the conditions of continuity of the flow, the long chains that made up the red blood cells, they break down, disintegrate. That is, the viscosity of the blood is obtained as much as possible in the capillary area. The viscosity of blood in the venules is already lower, that is, less than in the capillary network. So, well, let's take a short break, and after the break, the nature of the flow, and the next parameter is blood pressure. The next issue that we are considering is laminar and turbulent flow, and accordingly, a quantitative criterion that allows us to determine the nature of the fluid flow. This is the so-called Reynolds number. So, there are two types of laminar turbulent flow. Laminar flow is the flow of not all particles with the same velocity. This flow is layered. In other words, look, the diagram shows that the speed of movement of the liquid layers inside the pipe or along some fixed plane. The speed may be different, but the speed of movement of particles inside the layer does not change. That is, they move one at the same speed. The direction of movement, that is, these arrows here, they also do not have to be straight. Acceptable bends, minor of course, not sharp turns, but nevertheless. That is, when the parallelism of the movement of these arrows is maintained, that is, a laminar or layered flow is a flow that is provided with the same pressure along the pipe section. A turbulent flow is a vortex flow or a current in which neither the speed of movement nor the direction of movement is preserved. That is, each particle of a liquid behaves in a complex way. That is, not only can it move from layer to layer due to the fact that it changes, it is allowed to change the direction of movement. These layers, of course, can have different speeds of movement. We are interested in laminar turbulent flow simply insofar as it is believed that normally the nature of the blood flow should be laminar. Laminarity is one of the conditions for the movement of blood flow through the vascular system to minimize the load on the heart, respectively. That is, the heart, working as a pump, pumps the same volume of blood and the energy that will be spent on moving. Provided that the flow is laminar, it will be one value, And if the blood behaves competitively, that is, it moves in external flows, then naturally the energy that will be spent from the heart, it should be many times more. In order to quantitatively characterize the nature of the flow, the Reynolds number is used. Here is the calculation formula of the Reynolds number. The letter Re is indicated. It depends on the density of the liquid. It depends on the linear velocity of the fluid flow, well, or blood in the end, we will say. Depends on the diameter of the pipe or on the size of the lumen, and naturally depends on the viscosity of the liquid. Each fluid has its own critical Reynolds number. In the case when, well, for example, the critical Reynolds number for blood is 1000, the critical Reynolds number for water is 2500. If, well, the formula for the Reno number has already been calculated, accordingly for these conditions, for this section of the pipe, for this blood, and the specified, more precisely obtained number. If the specified number exceeds the critical number, then the movement in this section of the pipe is considered to be turbulent. If the obtained number is jealous, it will be less than the critical one. Then it is considered that in this case the treatment should be laminar. In other words, it is possible to simulate the parameters of the vascular system in advance, so that it is possible to choose the appropriate materials, the appropriate parameters, in terms of the diameter of, say, a vessel being replaced with some kind of artificial area, and so on. The reasons for the transition of laminar blood flow to turbulent are many different factors and reasons. First of all, it is an increase in the speed of blood flow. That is, with, let's say, excitement and stress, with significant physical exertion, the speed of blood flow increases. Therefore, the energy that the body expends on moving this volume of blood through the vascular system increases. That is, the blood moving turbulently, as I have already said, requires a lot of energy from the side of cardiac activity. The second reason for the decrease in blood viscosity is observed in anemia, that is, for example, the number of red blood cells decreases, the viscosity decreases, and then the transition of the laminar flow into a turbulent one is more likely. Or, for example, with an increase in body temperature. The blood moves at a higher speed, the viscosity decreases and transitions are possible, more likely, more precisely transitions from a laminar flow to a turbulent one. As a result, again, the load on cardiac activity may increase. The third reason for the increase in blood density. Well, this may be due to the same increase in temperature. That is, just when moisture simply evaporates from the body and the blood loses moisture, including, and in general, the composition of blood, the ratio of shaped elements and blood plasmas. It also affects the possibility of transition from blood flow to turbulence. Well, one of the most typical reasons for the transition is a change in the diameter of the vessel. Here are two pictures in front of you. In the first picture, the reason for the decrease in the diameter of the vessel, the lumen of the vessel is, for example, cholesterol plaques, that is, when the vessel overgrows from the inside, and, accordingly, when passing this narrow section, the blood moves further with a more likely turbulent flow. That is, a swirl is formed after passing the place of narrowing. And the second reason is vascular spasm. That is, a sharp narrowing of the vessel lumen, well, due to external factors. Here, too, pay attention. The blood, having passed the place of narrowing, then slows down the movement of red blood cells, and move in other directions relative to the previous one. That is, here is a transition to a turbulent flow. Here it is an increase in energy to move this fluid at the same speed, to preserve the continuity of the flow, and as a result, the growing energy that the heart expends, moving the same volume of liquids. That is, there are plenty of reasons for the transition from the normal laminar nature of fluid motion to turbulent. And now we are moving on to the second block of parameters characterizing hemodynamics. This is pressure. Blood pressure, in particular, can be described using the Gauguin-Pose equation. This equation, which contains Q, is the volumetric velocity of the fluid, or the volumetric velocity of the blood flow. This is the next important parameter, which is the pressure difference. In other words, this is the very reason why, strictly speaking, the movement of blood in the body takes place. In general, the fluid movement is caused by this pressure difference. P1 is the pressure that the heart sets. That is, the work of the heart determines this pressure. And P2 is the pressure that can be measured at any other point of the cardiovascular system. The multiplier that stands, the large multiplier that stands in front of the brackets contains, so to speak, characteristics indicating the properties of blood and the parameters of movement. Here, the movement parameters include the radius of the pipe, or the radius of the vessels, and the characteristics of the L. L is the length of a pipe or the length of a vessel, and in the denominator there is also the viscosity coefficient. That is, it is something that relates to the characteristics of the moving fluid itself. In other words, knowing these parameters and expressing N2 from this equation, it is possible to calculate this pressure, I repeat, at any point of the cardiovascular system, or simulate it, depending on what goals are set for this or that researcher. The multiplier that stands in front of the bracket, this very cause of fluid movement in a closed system, is the so-called hydraulic resistance. Well, generally speaking, the value is the inverse of this multiplier. The hydraulic resistance can be remembered by analogy with the electrical resistance, if you remember. The hydraulic resistance is determined, well, again, by the viscosity of a non-moving fluid. The length of the pipe or vessel section. Well, this is a constant, and in the denominator, this strong dependence is the radius of the pipe, or the radius of the vessel to the fourth power. That is, the maximum dependence of the hydraulic resistance. This is a dependence on the lumen of the pipe or the lumen of the vessels. That is, reducing, for example, the radius by half will lead to the fact that the hydraulic resistance will increase 16 times. That is, 2 to the fourth power. Therefore, many medications, for example for hypertension, are aimed at removing or reducing arterioly spasm. Here is a graph of the distribution of blood pressure in a large circle of blood circulation. And before we start analyzing the graph, pay attention to this point. That is, point 0 on the graph. It's not an absolute vacuum, it's just atmospheric pressure. That is, today, for example, our atmospheric pressure is 710 millimeters of mercury. Therefore, this is our starting point. And that the blood pressure that we will change, is actually the pressure that exceeds the pressure of the atmosphere at the moment. "120 millimeters of mercury column" means that the pressure during systole, we have 120 millimeters of mercury column above atmospheric pressure, for example. So, normally, yes, the well-known known norm is 120 to 80, the so-called lower systolic, diastolic pressure, and it is marked on the graph in the form of a grid. In other words, these pressure fluctuations, they are, of course, noticeable in the area of the arterioly artery. That is, up to the capillary network, these oscillatory movements or pulse are being listened to. Clearly, so to speak, there is a pressure difference between systoles and diastoles. Well, let's move consistently. So, it means that during systole, the corresponding volume of blood is pushed out of the left ventricle under pressure. Well, if this is normal health. Under the pressure of 120 millimeters of the turbid column. Making oscillatory movements, we observe, look at the dotted line, we observe a gradual drop in pressure in the arteries. The pressure drop increases as we move away from the heart. And again, the maximum pressure drop is observed where this very maximum branching occurs. That is, the passage of the arterioly artery, and the very movement of blood through the arterioles is also a sufficient load on the heart, a lot of resistance from the stationary walls of the vessels, and, accordingly, a significant drop in pressure. That is, while you look, the pressure behaves approximately the same as the speed from the aorta to the capillary. This is a directional decrease in this parameter. And the reasons are still the same. That is, the further away from the left ventricle, the lower the pressure. A sharp drop on the arteries, because these are long, thin vessels, because the volume that fills the blood increases sharply, and the heart has to push the same volume of fluid through these branching vessels. Vessels, I mean arterioles of small diameter, but long enough. Here, the exchange between the moving blood and the tissues is already active. The pressure drop continues in the capillary area. That is, under the condition of a minimum blood flow rate, the most active exchange between the blood and the capillary walls takes place here. But then, unlike the velocity graph, there is a different direction of change in the pressure graph. The pressure in the venules and veins continues to fall. Here we are moving further from the heart and the further from the heart, in the sense that the further from the left ventricle, closer to the right atrium, the lower the pressure. That is, kinetic energy is wasted as the blood moves, as a large circle of blood circulation closes. And finally, look, when you reach the hollow veins at this point, the pressure becomes so-called negative. Negative pressure in our case. Remember that zero is atmospheric pressure. That is, negative pressure is a pressure that, well, this zero means that the pressure becomes equal to atmospheric pressure, and below all that is below is negative pressure. That is, the pressure in the hollow veins is even less than the atmospheric pressure. But a large circle of blood circulation nevertheless closes, and this closure is caused by the suction movement of the chest. That is, our breathing movements allow us to close the circle and deliver blood from the hollow veins to the right atrium. Next question. Well, just for general development. That is, how exactly can systolic diastolic pressure be calculated according to age? If you want, write it down for yourself. And so, of course, focusing on the value of 120/80 is not quite right, not quite correct for people of different ages. The next slide that we are considering is the factors that determine or affect blood pressure. Look at these factors grouped into three blocks. The first block is the factors that determine the pressure set by the work of the heart. That is, the very factors that cause the movement of blood through the vascular system. That is, the heart, working as a pump, pumps pressure initially, under the influence of which the blood moves. The second group, or the second block more precisely, of factors are responsible for the exceptional elasticity of the vessel walls. That is, the state of the vessels at the moment. And the third block is the resistance experienced by the moving blood through the vascular system. Returning to the pressure to the first block, that is, factors that affect the work of the heart. Regardless of age, this is a muscular load. This is the presence or absence of emotional stress. And, of course, these may be functional changes in the work of cardiac activity in general. That is, how well the heart copes with the task. It all depends on. This is all included, so to speak, in the first block of factors that determine blood pressure. Further, the elasticity of the vessels has a significant effect on the pressure that we can determine there in some patient at a particular time. So, well, first of all, the condition of the vessel walls is determined by the presence or absence of these sclerotic changes. The greater the erotic index, the fewer elastic vessels. Age is simply already one of the reasons for reducing the elasticity of the vessel walls. That is, the state of this parameter with age, it is already almost unambiguous. In other words, the walls of blood vessels become more rigid, thereby changing the parameters of blood pressure, since through rigid systems the heart has to move the same volume of blood through the circulatory circles with a greater load, work with a greater load. And finally, the general resistance experienced by moving blood through the vessels. This is the radius. I'm sorry, I can't attend the lecture. First of all, the total resistance, hydraulic more precisely. The resistance is determined by the radius of the vascular bed. The smaller the radius, the greater the resistance by the length of the vessels, that is, the general path that the blood travels through this thin or narrowed vessel, and, of course, the viscosity of the blood itself, that is, the composition of the blood, by changing which, we can also eventually change blood pressure, also adds up to one of the reasons for the change in the factors determining blood pressure. That is, any of these points, a change in any of these points, leads to a change in blood pressure. Changes may be more systolic, less diastolic, someone may have the opposite. That is, in general, a lot of external influences, internal leads to the fact that blood pressure fluctuates. And in general, nowadays blood pressure measurement is used in the diagnosis of almost all diseases. Blood pressure can be measured in two ways. This is the so-called direct method and indirect. The direct method of measuring blood pressure is the only method of measuring pressure in which a needle connected by an osmonaut is inserted into a vessel there or into the heart cavity. Well, that is, with a pressure measuring device. This is a very accurate method of measuring blood pressure. Well, of course, in order to directly measure the pressure, since the pressure is measured, let's say, in car tires, it is necessary to violate the integrity of the vessels. These methods are used when pressure is measured, for example, for scientific purposes, or when there is some serious intervention on the heart and then the pressure in the cavity of a particular cardiac cavity is measured directly. The most frequent and most common way to measure blood pressure is indirectly. It is mainly based on the clinical method of Korotkov. Korotkov is a surgeon who suggested the sounds that he listened to before deciding to amputate a limb. He was a military surgeon. He systematized these sounds and eventually suggested that they be considered as, well, some signals for pure, some signals for diastole. Well, in short, the essence is to listen to the sounds and noises that occur when blood passes through the brachial artery compressed by the cuff. That is, the cuff is superimposed on the arm between the shoulder and the elbow, pumps the cuff air until the pressure in the cuff becomes about 20 millimeters higher than the main column there. At the same time, the pulse on the artery below ceases to be felt or listened to. Well, that is, the artery is completely squeezed. Then gradually reduce the pressure, that is, they release air from the cuff and register the sounds that appear. And these sounds, I repeat, relate either to systolic pressure or to diastolic pressure. That is, when the pressure in the cuff is greater than the pressure in the artery, the brachial artery, then the blood stops. You see, the vessel is completely squeezed. We don't listen to anything with a panodoscope. Well, or now semi-automatic, automatic pressure measuring devices do not record anything. This is the condition of a completely clamped artery. When we start releasing air, that is, we gradually bleed it off. Then look what happens. At the moment of systole, the vessel opens. At the moment of diastole, it is captured again. Well, that is, it sticks together. You can say that. That's why the blood that comes in portions, that is, it comes in jerks only at the moments of maximum pressure, and correlates with the systolic pressure by Korotkov. In other words, those knocks or tones that we hear at the very beginning, when the pressure is released, are sounds correlated with the pressure during systole. That is, during a higher pressure, the vessel opens slightly, passes a certain portion of blood. So, I repeat again, this is systole. With a further gradual decrease in pressure in the cuff, the tones are supplemented by noises, which are accompanied by a turbulent flow of blood through a partially clamped section of the artery, continuing to reduce the pressure, that is, releasing air from the cuff. Then, the moment of tone termination is recorded, and the diastolic pressure corresponds to this moment of termination. That's how Korotkov also suggested counting, that is, The last tone is a diastole. The first knock, according to Korobkov, is systolic pressure. The last knock, after which this pulsation disappears, the knocks disappear. This is the pressure during diastole. That is, the readings of the pressure gauge in this case show that the laminar flow has been restored. Well, the standard pressure measuring device consists of three main parts. This is a cuff, the air pressure in which is considered approximately equal to the pressure in the artery. That's why the method is called indirectly. Because in fact, well, look and remember the pressure gauge, that is, a pressure measuring device, it is connected to the cuff. That is, the pressure is measured in the cuff, not in the vessel. Well, I repeat, since it is believed that the pressure in the cuff is approximately equal to the pressure in the artery, then it remains only to compare the sounds that this artery reproduces depending on the condition. Completely blocked, partially blocked, completely restored. Well, the pressure measuring device contains a pair or some kind of automatic air blower, a semi-automatic pressure gauge, or in old manual devices. It's just a device. A typical pressure gauge is round with an arrow, or in modern, it is a scale that shows not only the pressure, but also the pulse, for example, but also a phonoendoscope, or a device that listens to sounds, or records sounds that appear below the cuff overlay. That is, according to the fact that what happens to the cuff and certain sounds appear, which we, well, or the devices already automatically correlate either to systolic control or to diastolic control. And that's the end of the lecture.